this week we have Stephan Kreutzer from TU Berlin, who sent us at least 3 postdocs to Thailand.
And Ghana.
And Ghana. Right? So father of 3 people here. Yeah, I'm very pleased that he's visiting here and talk about paths, right?
Yeah, thank you very much. Yeah, let me return the compliment. So, thanks for inviting me here. I learned yesterday evening that apparently I hold the record for sending the most postdocs from any foreign, non-local group, obviously. And now that I'm here, I can see why they all like to come. So it's very special what you built up here. So it's, thanks for inviting me and giving me this opportunity to speak. So,
Yeah, middle button, yes. And that's later.
Oh, it's a bit delayed. No, I'll make a. Okay. Yeah. So I want to talk about disjoint path in graphs and directed graphs. Most of what I want to say is about directed graphs, and the point of this talk is not so much to give you one specific result that we proved and I'd like to explain, but instead sort of give you some feel for what the problems are in directed graphs and what the techniques and methods are that we developed, we meaning the entire community in the last couple of years. So what is the problem? Well, we're interested in computing pairwise-disjoint paths. Yeah, so we're given a graph, a directed graph, doesn't matter really, and then we have a set of source vertices, S1 to S4 on the side here, and we have some targets, T1, T2, 3, and so on. And the problem is that we want to decide or compute, if they exist, a set of pairwise-disjoint paths, let's say, P1 to Pk, so that the path Pi links the source number I to the target number I. Now there are many variations you could look at. We can have graphs or digraphs. We also have some flexibility what disjoint means, so it can be vertex or edge disjoint or other things. And later on we see an even looser concept here. And this gives, but they all give prompts of a similar flavor. Okay. But let's start with vertex-disjoint path in undirected graphs. Now, so what do we know about the complexity of this problem? Well, so Menger's theorem, which I assume you heard of, just tells us if you don't particularly care about the order in which the sources are linked to the targets, so all we care about is whether we can find k path, each linking one source vertex to some target vertex, then this can be computed in polynomial time if they exist. Yeah. So we're just asking for path from the set of S of sources to the set T of targets. Sorry, I'll try my luck with this thing again. Yeah. And if these paths do not exist, then we get a counter, so a witness for an obstruction, namely separation here. Sorry. What's going to go back?
There's a button on the bottom.
Right. Yeah, okay. And the obstruction, okay, I can't find it. Just we get a separation here of order less than k, so few of the k vertices that separate the left from the right. Okay. But that's not exactly what we wanted, because in the original statement we were given a tuple, let's say, S1 to Sk and T1 to Tk, and we wanted the path Pi to link really the source number I to the target number. Right? And that's not exactly what we got. And this problem is a little bit harder. In fact, it's significantly harder than the just Menger style, can you go from the set S to the set T problem. And in fact, it's NP-complete, and I think this is one of the early NP-complete problems. If you get this as input. But it's not the end of the talk, so there's more to come. Yeah. Because then Robertson and Seymour proved that on undirected graphs, the problem, the k-disjoint path problem, is fixed point tractable. So it means there's an algorithm solving it, and the running time is bounded by some function in the number of terminal pairs, and a polynomial dependence in the size of the input. So this function here is not particularly small, at least initially it wasn't particularly small, and it's getting smaller now, but we don't care about this, so it just means for fixed value of k, you have a fixed degree polynomial diagonal. Okay. So, yeah. Let's look how this works quickly. Yeah? Let's give some rough idea how this algorithm works. So we have our graph, and we have our sources and targets here. Now, the first thing we can obviously do is just apply Menger's theorem and just ask, do we even have k-path from left to right in any particular order? We don't care about the order at the moment. And obviously, if the outcome is no, we don't even have any k-path from left to right, then obviously we also don't have k-path in the correct order, right? So the answer is no right away. And we can solve. And this we can decide in polynomial time. Or what if the answer is yes? So Menger will give us k-path, but they're not connecting the right terminal pairs. So, what we have to do is kind of reorder the path, so that they, well, like this one here, that goes from S2 to T3, you have to reorder it so that it will end up here, and the first one then has to go here, and so on and so on. So how can we do this? Well, if that's what we want to do, just change the order in which these paths arise here. It would be nice if somewhere in the middle we had a kind of routing device, whatever this is for the moment, so that the path goes through this thing, and in here we could sort of rearrange them in any particular way we need. So that certainly would be useful to have. Well, I haven't specified what the routing device might be. But clearly, if this was, let's say, if this path were to go through a large clique, for instance, that would probably be a useful thing to have. So maybe let's look at this first. So suppose for the moment that we have a graph, and it contains a subgraph H, which is isomorphic to a clique on at least 2k vertices. So this thing here seems on the edges of it. Now I could ask Menger again, or let's say I apply Menger's algorithm. And what I'm asking for is, can I find 2k paths that connect S union T, so just a set of all terminals, to the vertices of the clique? And I don't care about the order. And if the answer is yes, then we are done, right? Because it tells me I can route the sources here to vertices of the clique and the targets as well. Yeah. And then I can connect them as I need them to be connected using the edges of the clique. Right? So this path from S1 goes here. It has to continue this way, but there's an edge between these two vertices. Right? So that's certainly a win, because the clique allows us to get the right order. But we also win if the answer is no, because then Menger's theorem will give us a small separator. And so every path from source and targets to the clique will have to go through one of these vertices, and there are fewer than 2k. Right? Well, what it means is, well, if you want to use the clique for anything, well, we have to start somewhere, then use a vertex of the separator, go to the clique, and then come back. Yep. So you're using at least one or two vertices of the clique, of the separator, of any path we want to route. Yep. But these are fewer than the number of vertices we have in the clique. And so truly what's enough is if we just pick 4 paths, one for every vertex in the separator here, to the clique, let's say pick these 4 paths. And then whatever we can achieve on this side, we will not be needing the last 4 vertices of the clique. Right? Because whatever we can achieve, we can do with these vertices. Which means we can just delete the remaining vertices of the clique, we get a smaller graph, because we lost the vertex at least, and we just start anew, we recurse on the smaller graph. If we keep on doing this, eventually the graph will be small, and we will do something else. Right? Okay, so having such a clique is a win-win situation. In any case, we win, and this can be computed for a longer time. Now, the clique, of course, is a very harsh requirement, and we can loosen this a little bit and just say, instead of a clique, we have a clique minor. Then things get a little bit more complicated, but in principle, the same approach works and gives the same outcome. Okay, so large clique minors are good. So the question is what happens if we don't have them. And this is actually what Robertson and Seymour then spent most of their time proving. So they had a nice and powerful structure theorem for a graph that excludes some fixed size clique as a mind. It's kt, in our case t would be 2k. So what we essentially prove is for every graph either you have a large clique, this is not so large in this picture, assume this to be kt, and if you don't have it, then the only reason for this to be is that your graph looks like a tree, similar to a tree, which is formalized, which they formalized by the notion of tree width. Your graph is more tree width, and we can solve almost everything very efficiently. And the complicated part is what happens if your graph does not look like a tree, so the tree width is very big, but we don't have a large clique minor. And then they prove that essentially you have a decomposition into pieces which we can embed on the surface more or less. But for us, what's interesting is we are then guaranteed that we have a large subgraph of our graph, which we can embed on the surface. And the genus of the surface depends only on t. And this subgraph contains a large grid. So this grid-like thing. It's a graph like this. So we have vertices and all these crosses, and then the edges containing it. And this is flat. It's called the flat wall theorem, or the flat wall, meaning the rest of the graph attaches nicely to the grid. So essentially, if you want to move from outside the grid towards the grid, then you have to go through its outer cycle. And this is for the embedded part. And then we have some special regions that we call vortex. And the part of the graph that are not drawn here, they attach only through these vortices or in a very, very controlled way. Look, just some exceptions we call APCs, but there are few and don't care about. So why would we care about this? Or what can we do in this case? Well, so let's zoom into it. And so what they proved is what's known as the irrelevant vertex theorem. And so this is just what I explained in informal writing. So we have the situation, so the rest of the surface is here, and this is a large grid. Now, suppose we had a solution to our problem. Let's say we have a terminal here that we need to connect, I don't know, maybe here, and maybe green is not the best choice. Let's choose blue. And we have these blue terminals that we connect. And maybe the solution looks like this. Like this, and then the blue thing is doing. Maybe the solution uses the entire grid. But if you think about it a little bit, then why would it be like this? I mean, okay, this red path, it has to make a detour to avoid to go around the blue terminal here. But why would we be doing such kind of things? Because we could immediately, at this point, it's a grid, we could go this way and shortcut. In fact, go this way and shortcut. We could go this way and shortcut. And what we see is we also get a solution which avoids most of the grid. So one of these bits are off. And you can prove that if your grid is big enough, then you can always reroute any solution to avoid the inner pieces of your wall. Right? And that means if you have a solution, then you also have one that doesn't go through the inner vertices, and if you're guaranteed that there's a solution without using it, then delete it. Right? And that's the same, that's what this approach is doing. The hard proof is that you can always avoid the center of the grid, and then once you found it, you just delete it, get a smaller graph, recurse, and be happy. Now, this was a very short and brief sketch of what happens. If you want to learn more about it, then Max gave a very nice talk about this just a few weeks ago in this seminar, and you can look it up at YouTube. And he gives you all the history, all the details, everything you ever wanted to know in this talk. That's it. Good. Right. So that was about undirected graph, but I advertised that most of the graph would be, most of the talk would be on directed graphs. So maybe it's time to move to digraphs. So what can you say about this? Well, Menger still works, right? So there's a directed version of Menger's theorem, which says we again have the same setup. We have sources and targets, but now we want to use directed paths that start here in the source vertices and end in the targets. And we can still use polynomial time algorithms and network flow things to just check whether we have 4 paths in this case, from left to right. Yeah. If you ignore the order in which they arrive at the site. And if you don't have these 4 paths, then we have a small separation, which would small separator separating left to right. Yeah, this is good. So that's the same as in the undirected case. But if you paid attention so far, then you may remember that there was a little bit more than this to Robertson and Seymour's algorithm. So let's see what remains of this picture in the directed set. Okay, we have this large click minor thing, ignore the minor part, and maybe we can use a bidirected click. Okay. Then we have this notion of tree-like graphs, and there is in fact a version of it for directed graphs, which was introduced by Johnson, Robertson, Seymour, and Thomas in 2001. They define the notion of directed tree width, which is more or less direct translation of. The definition is very similar to tree width on that. So in tree decompositions, the edges form a separator. In the undirected graph, in a directed tree decomposition, they form a strongly separator, so they would separate strongly. Okay. So that's also okay. For this bit, here I said we had a flat wall theorem that guarantees us that we have an embedding and the whole structure theorem into surface and so on. There is a directed flat wall theorem that we proved a few years ago. Several co-authors. The bit with the structure theorem doesn't really work. So it doesn't exist, and it's not even clear what it exactly it would look like. So what it means is what we can guarantee is that if you have high directed tree width, you find a large directed wall, and I'll explain in a second what this is, to which the rest of the graph mustn't hit from the outside or something very controlled. But the embedding part is missing. Okay. Another one. Yeah, so at least we have some ingredients of the undirected setting, but it doesn't work so well because because in 1980, Fortune they proved that the directed disjoint path problem is NP-complete even if all you want to do is connect 2 terminal pairs. Yeah, so we don't even need 4, just 2 pairs is enough. 1 obviously is trivial, yeah, it's just reachability, but 2 is the first non-trivial one, and it's already NP-complete. Okay, this sounds a bit bad, but somehow it doesn't explain why it's so hard. Right? It's a reduction from satisfiability. It's really perhaps using a very, very clever gadget that allows you to switch and mimic sort of assignments to propositional variables. So it's a clever gadget that uses it, but it doesn't really tell us why the techniques that we used here actually fail. I mean, they have to fail, obviously, unless B is the same as NP, but why exactly? So let's look at the first and simplest case that we, sorry, this is important, I forgot. So this simple, the NP hardness for routing 2 terminal pairs immediately implies that the following problem is also NP hard. So what you want to do is you want to start at the vertex S and go to T, and in the middle you want to visit some friend, yeah? So vertex u. And deciding whether you can do this is also NP-complete. And this is a very, very simple reduction from the k-disjoint path problem.
Yeah. So you don't allow visiting same vertex
No.
twice?
This has to be one path,
Ah,
not
it's
a
the
one.
path. Okay.
Okay, if you allow this bit to intersect this bit, then it's not so hard. Yeah? It's reachability, but if you want these to be disjoint, so the whole thing gets one path, then it's incomplete. Yeah. And I'll need this in a moment. And the reduction is very simple for this part, right? You just add an edge from T1 to S2 and delete all the other edges, and then the only way of getting from here to here is basically by having to disjoint. Okay, good. Yeah, but let's look at the simplest case for the undirected setting. Namely, we can apply Benger to ask, do I have path from S to T, and we need to reroute them. So let's suppose we have a directed graph, and we have a large biclic. And the biclic is just a set of vertices between any pair of them edges in both directions. Now, we can again apply Menger's theorem just to check whether we have k-path starting in the sourced vertices and ending in vertices in the click. Okay. And we can apply it again to check whether we have k-path from the other click vertices back to the targets. Right? So this we can do in polynomial time. The problem is we can't do this simultaneously. Right? So we can't ask Menger, can I find, but at the same time, completely disjoint path, 4 of which going this way and the other 4 going that way. Right? And because we can't do it, it means the paths which are disjoint from S to the click and the ones that go back, they may intersect between themselves. Right? And somehow it seems like you can't really avoid it because you've seen this here. Even asking for one path from S1 to go to the click and back is an NP-complete problem. And of course, it won't be easier if you're asking for 4 paths simultaneously. Pairwise disjoint. So there's a bit of a problem, and this problem appears everywhere, and it's really annoying. But what can you do? That's the way it is. Okay. Still, coming back to it. Maybe we can do a little bit more than just stop here and have dinner. Yeah? Because maybe can achieve better results for other classes. So let's look at a few more cases. So if we only consider acyclic directed graphs, so no cycles, then the problem can be solved in time n to the O of k. So if you know about parameterized complexity a little bit, this is called an XP algorithm. So for the FBT algorithm, we wanted something that runs in time f of k, and then some polynomial in the input size. And Swift proved that this is unlikely, so with the usual assumptions in complexity theory, it's unlikely to exist. Yeah? But the next best thing perhaps would be what's called XP. So it's n to the sum function of k. Yeah? And this exists, and in fact this function is just a linear function. Another case is the notion of directed treewidth that was introduced by Johnson, Robertson, Seymour, Thomas, that I already mentioned. And this in a way generalizes directed treewidth, but it has the property that acyclic digraphs, because they don't have any non-trivial strong components, they also have very small directed treewidth. And what they showed is that the problem can be solved in time in XP. It's n to the some function in directed treewidth and the number of terminal pairs, but it can't be improved to an FBT algorithm. But maybe let's not worry too much about FBT. Yeah. So it goes. Let's just say what we're interested in is an algorithm like this. So in other words, what I now want to find is, if I fix the number k of terminal pairs, do I then have a polynomial time argument? I don't really care about how this k goes into the polynomial, but for fixed k, there should be polynomial. And this exists if you bound the directed tree. Okay. Yeah, so these are some cases that work, and there are some more. Yeah, but, so if you come back to this hardness for k-terminal pairs, yeah, then there's no hope to prove such an XP algorithm for general digraphs. So we have to do something, and we have various ways of simplifying the problem a little bit. So one simplification we could look at is what's known as the half-integral disjoint path. And it's a little bit motivated by this problem. Yeah? So we had a way of getting disjoint path from S to tick. We had a way of getting the black disjoint. But somehow we couldn't control how the black and the blue path would intersect. So maybe things become easier if we allow two paths to intersect. So we're looking for k-directed path from connecting S1 to T1 and S2 to T1, T2, sorry, and so on. But now we allow that the vertex appears in two paths, but not more. Yeah? So no three paths should have a non-empty intersection, but we allow two paths to cross. So in this sense, in this case here, it would be, we would have a solution that we take these ones, then we reroute the bicycle, we go back, and because the blacks are disjoint and the blues are disjoint, no vertex would appear in three paths, and we are fine. Okay. So that would be one restriction to simplify things. The other one is the usual approach. Maybe we can look at smaller classes of directed graphs, like planar digraphs or Eulerian digraphs, and check whether we can find solutions there. Okay. But let's first look at the half-integral disjoint path problem. And it was conjectured, you have to work on it, it was conjectured that maybe this problem should be solvable in polynomial time for every fixed number of k. And there are some known results. So we had a even simplified version, which has the name is debatable, but what it says is it's called half-integral or no integral disjoint path problem. And it just means the positive solution should be a half-integral solution, or the negative answer would just be that there is no linkage connecting the sources to terminals. This simplifies, it may not be obvious why it's easier, but it simplifies it a lot. Okay? And for this problem, we can prove polynomial time algorithm for every fixed over k. Then for the half-integral disjoint path problem, there's efforts that are, they prove this conjecture here, but in the restriction to, they had to assume that their input directed graphs are very highly, strongly connected. Yeah?
For the half integral or no integral, you said polynomial time algorithm for every case is XP still?
It is XP.
Okay.
Yeah, it's XP. I mean, all of this is XP because even in directed trees it's XP,
Okay.
and we use at some point directed tree. So it would be not XP up to the point where it's supposed to be simple, namely directed tree is small, but then it's XP. Yeah, so efforts, they proved this for efforts we see in volume for highly connected, so highly strongly connected directed graphs. And then there were various improvements to these, bringing the connectivity requirements down and so on. And people worked on, and I think it's fair to say, I have annoyed and now a whole generation of my PhD students working on this to know positive result at the end. Okay, and we'll see why. So what we know about this half-integral disjoint path is it can be solved easily on Gauss-appointed directed tree. So by an XP algorithm, it can also compute directed tree decompositions in FPT time, more or less the same algorithms as for the undirected trees. So more interesting is what happens when the directed tree width is high. And Johnson and I, they conjectured a directed, so the directed version of the excluded grid theorem already here in this paper, but it took a little longer to prove it. And then somehow we can prove there is a function f, and this is not small, but it's 6, let's say. So every directed graph of directed tube, at least f of k, it contains what we call a cylindrical wall of order k. And the cylindrical wall, I don't know if you can see the arrows here, it's just a set of k concentric cycles all oriented in the same way. And then we have alternatingly a path going from the inside out, the next one goes in, out, in, and so we have k pairs of these paths going in the bed. And if you take it to a wall, so you split the vertices, you get something that looks like this, so the cycles go in the same way, and then you have these things that go. And the idea was that such a thing should play the similar role to grids. So maybe we can delete vertices, we can use it to reroute. In particular, in the half integral case, if you could route into such a thing and out of it, then maybe because you're allowed to cross, you could connect things into the grid. And this is the general proof strategy for the results that we've seen on the slides ago. They will try to do this in this way. You try to go from sources here to this grid, and then from the grid to targets, and then try to reconnect in here. So I tried to prove that you could also delete a vertex in here. This failed completely, but you can reconnect if the paths go into the grid and don't come in the same place. And the pre-assumption that the results I mentioned have of high or strong connectivity just means you will never have a small separation between the wall and the targets, and you can ensure that you can read it. Okay. But this really depended on some preconditions that allows you to guarantee that you can actually go from the sources different vertices in the grid and from the grid to different vertices here, so you can reconnect. If not, and you have a small separation, then we are in the same problem as before because we don't know how to handle this. And this kept us busy for a long time, same things, until last year. The reason we couldn't prove it is because it's actually false. And so for every number k bigger than 4, the half-integral k-Disjoint path problem is incomplete. So there's simply no way of avoiding these intersecting separation problems. The only case where it works is for 3. There we can use the approach on the previous slide to get it to work it out. So for half integral, of course, 2 path is trivial because 2 can intersect and you only want to, and it's easy to do. So this is the first non-trivial case, and it's also non-trivial to prove. What's open is the case for k equals 4. And we haven't spent an awful amount of time on it, but we spent some time trying to prove it's NP-complete, and some time trying to prove it's polynomial time. Both failed. We always ended up in exactly the same picture, so I don't know. I don't even know which way wouldn't even conjecture which way it goes. So, want a easy to state problem that you can look at and work on, then k equals 4. Maybe there's a simple solution that we missed, but otherwise it might be something to get entertained for a while. Okay, so that's the half integral version. Now let's come back to except for the k equals 4, then this bit is etc. And you can extend the hardness result to, if you allow 3 paths across, then you get the same for k bigger than 7. So it's 2k plus 1, I think. No, 2c plus. If you allow c path to cross, then hardness sets in at 2c plus 1. Terminal classes. Okay. Good. So that isn't going on too well, but we have the other route. Maybe we can look at restricted classes of graphs. And candidates that come to mind might be planar directed graphs, Eulerian digraphs, and other things not on the list. And indeed, for planar graphs, the k-disjoint path problem is fixed not tractable in the class of planar directed graphs. And this was proved by Seymour, Marx, and the Digraphs, both of them. And on a very high level, the idea is similar. So what they proved is if you don't have the cylindrical grid I do, but you have an alternating grid. So you have cycles in alternating directions, or embedded on the surface, or on the plane, let's say. And you have paths going in and out. Then you can actually prove a random vertex rule. So you can avoid, if the linkage goes in too much, then you can avoid a vertex somewhere in the middle, whatever the middle here really means. If you see, there's two boundaries. If you only have cycles in one direction, then you can't. There's examples that show you're kind of stuck. And then the rest of the, I think the other 70 or so pages of that proof analyze what happens if you don't have this thing. Because it's not the dual notion of directed treeless. Because the dual notion is just all cycles going in the same way. And it's not clear what the dual notion to avoiding this bi-oriented grid would be. I don't know. But for planar graphs, you can analyze them, what happens, and it's a long proof, but eventually they can prove this too. Yeah, this is nice. Very nice result. The other case now, and this is remaining hour and a half or so, I want to speak a little bit about Eulerian diagrams, and explain what happens there. And here I will be looking at edge-disjoint paths. And what is a Eulerian digraph? It's a directed graph in which every vertex has the same number of incoming edges as it has outgoing edges. So the in degree is the same as the out degree for every vertex. And this is equivalent to the Eulerian digraph just being the union of a set of pairwise vertex, pairwise edge-disjoint circles. Take the union of these and make a few Eulerian digraph. And this is a class of graphs that's, well, it's directed, but it's somewhat, it shares nice properties more similar to undirected graphs, at least some of them. In particular, if the degree is bounded, if you have a bounded maximum degree. And we'll see an example of why it's a nice mathematics. The theorem that I is that if you look at the edge-disjoint path problem in the Eulerian diagrams, then this problem is fixed not tractable. So edge-disjoint just means we're looking for paths from connecting Si to Ti and so on. But they don't have to be vertex disjoint anymore, but at least no two paths should share an edge. They can cross at the vertex, but not use the same edge. Okay. So here's how the proof goes. We've seen similar pictures before. Yes, so we have sources on the left and targets on the right, and we need to connect them. And we want to use the same idea as before, which I told you wouldn't work on directed graph. So, because Menger's theorem, of course, works everywhere, I can ask for 4 paths to go left to right, but I have to rearrange them somehow. So, I would like to send these 4 paths into the router in any form. It could be a clique, or it could be something that will allow me to reorder the path, and then I want to send them here. Okay? And then use the green part to connect them as before. Wait. I said, well, that won't work, right? Because even going from S to T, just fixing one vertex in the middle is not complete. So this approach shouldn't work. But for Eulerian diagrams, it's actually not. Yeah. And this is a very nice result by Frank. I've forgotten the date, 90 something. Forget about the date. Something. And he showed that if this is what you want to do, so you have some set of vertices x and another set of vertices y, and then you have a central vertex v. And what you want to know is, can I find a set of pairwise edge-disjoint paths, 2k of them, so p1 to pk and q1 to qk, and the pi's, so the path pi links the vertex xi to central vertex v. So just imagine this green thing to be one single vertex. and the Q path link V to the vertices in Y. Yeah? Then this can be decided in polynomial time. And you also get an obstruction if these paths do not exist. But this is more or less, yeah.
Do you have to have the same number of x?
No. It's just in my case they did. So he has he defines a pattern graph, and so these would be demand edges, and the numbers can vary. But the pattern graph either has to be the union of stars like this, so all go in or all go up, or they have to be parallel edges, and otherwise it won't work. But we really just need this for this bit. And this theorem is exactly what we were hoping to have, hoping to use, because whether it's a single vertex in the middle, or the router, we can transform this. And this allows us to just check simultaneously, can I find this path to the routing thing and this path out, and then allow us to reroute in the routing. It's not immediately obvious, but particularly because I haven't actually defined what the router is, but it's not so hard once you have the formal definitions. So that's nice, because then this routing thing will work. And we can now look at what happens if you don't have a router. So I don't want to define formally what a router is, because it can come in many forms, but it's just something that allows paths to cross. Clique would be an extreme case, but there are also many other cases. So what can we say about a Eulerian digraph that doesn't have such a router? Well, one special case again is, well, G may just be like a tree. So like it has a directed tree with, which for bounded degree Eulerian graphs is more or less the same as having undirected tree with small. But for these graphs you can solve the problem easily. So now what happens if we don't have a router and we don't look like a tree? So the directed tree is this high. But then we can apply the directed grid theorem, and we guarantee to find this cylindrical ball. But now it's Eulerian digraph. Yeah? So if you look at these degree 3 vertices here, like this one, it has these two incoming edges and one outgoing edge. So it must also have another outgoing edge. Yeah? And we can now look at where would this edge go. Yeah, so maybe we have the cycle here. Yeah, and here are the two outgoing edges, and then incoming edge like this. Yeah? And this has to go somewhere, right? There's another edge. It could be going here, or it could be going here, and so on. Yeah? But we can just follow it until it hits the wall again. Right? And here's another special case, which is very specific to embedded Eulerian digraphs. And what if, let's say, the moment our graph is planar, and we had a planar drawing like this. Right? So these two incoming edges form one side of the, if we draw a circle around this around this thing, then the two incoming here, and the two outgoing edges. Then this is perfect for us, right? Because here I can use it to cross path. You're only asking for edge disjoint path. So if I have a blue path coming in one edge and the red path coming in the other edge, I can freely decide which path goes where. Yeah? The red can go like this, they cross. Or of course I could also set blue down and red up. Yeah? So if you have an embedded graph, a planar graph, Eulerian graph that has many vertices like these, then this gives us tons of crosses. Everywhere we can cross. And so if you have many of these, so if you look at this planar thing, and we follow the missing edges where they go, if you have many that are embedded like this, then we immediately get a router. Because you can cross, it's like a grid if you know the undirected case. If you have a large grid and you have many crosses everywhere, then you get a clique miner, and something similar happens here. So that's nice, and then we are done, because we have a router and we know what to do. The other outcome could be, well, what if they are all embedded in the other way, that we call Eulerian embedded. And so, by the way, I'm just talking about degree 4 graphs for the moment. Yeah? there are reasons why that's enough. So we only have to worry about two incoming and two outgoing edges. But if they come like this, so they alternate, incoming, outgoing, the trick won't work anymore, right? So if I now have a blue and a red path coming in, I can decide whether the red goes this way or that way, but they will never cross. Right? So if the red goes right, then blue goes left, they would still be on the same side. Which means such a thing would be really like an undirected grid in the vertex-disjoint case. You meet here, but they would not be able to cross. And what we get is what's called a swirl. We can prove if, unless you have these many strongly planar vertices, then we get this thing, which is just a set of concentric cycles going this way, and in between two cycles going counterclockwise, the other cycle going the other way around. And this is exactly the alternating grid that we already saw. It was a useful thing because I can reroute freely in this. And that is the key to the algorithm. So if we assume that we have a Eulerian directed graph, we don't have a large router and high directed tree width, then the extruded grid theorem gives us this large wall, and as we saw, if we don't have a router, I get this large swirl thing. And for Eulerian diagrams, there's also a structure theorem. So a version that was proved in Johnson's thesis already, if you know this. And we also proved one. It gives us theorem, and what it says is essentially, we know that we have this large swirl, so we can start drawing on the surface. Here it's just alternating cycles. Additional from the terminal things. And if you want to draw the rest of the Eulerian graph, then we have to cut perhaps some holes into the surface and glue in what's called bounded depth vortex. And don't worry what it is, it's just some controlled structure that we want to deal with. And yeah, the rest of the graph will attach here or nicely. There are no APCs because we have degree 4, so we don't have to worry about them in case you were wondering where they disappear. And so we can start with one embedded subgraph like this and try to tame a solution. And so we assume that there is a solution, and we assume that it's using all the edges. It's leaving aside technical details. The first step we can do is we can prove if there's a solution, then there is one that doesn't really go into these vortices too often. So go in and out a little bit, but not too often. Which means this is not entirely obvious to see, but this is the idea. If you know that the solution goes only a few times in here, we can just delete the vortex and replace it by terminals, so the vortices are gone. And then once they are gone, we have an embedded graph really. We can show the irrelevant vertex theorem that the solution wouldn't have to go through this swirl too often. You can always reroute it because you can go either way. You can reroute to the side. And then delete the inner cycle. In the Eulerian diagrams, you can never delete the vertex. You can just delete the cycle, the edges of the cycle. And have a smaller graph and recurse. And that's the entire setup. Okay, and putting things then together gives us an FPT algorithm for Eulerian directed graphs. Okay. Good. So that's the sketch of this proof. So to sum up, so we've seen some complexity results in the directed-k-Disjoint path problem, and what we've seen is that in the directed setting, the problem somehow becomes intrinsically and significantly harder than in the undirected case. Yeah? There are many reasons for it, but one is you have all this intersecting path and you don't know how to move them apart somehow. This hardness works two terminal pairs, and even if you relax this condition, the disjoint path considerably remains hard. But for interesting special cases, we can get But you can ask, of course, what we know. It's one final FPT algorithm, XP algorithm for all digraphs by Care. I also think that there's a nice connection between sort of studying disjoint paths and looking at the structure of graphs and digraphs. It's obvious for the undirected case, where the whole structure theory was used to prove the disjoint path thing, but it's also true for the directed case. The structure is not as nice, so far, but it's a nice connection. But it's also filled with plenty of problems. We'll just name very few here. One obvious thing is the often do case for k equals 4. Another thing that we are working on is to extend the planar FPT algorithm to larger classes of directed graphs and just see how far it gets. But there are many other. And I haven't mentioned the entire field, so there's a whole sort of routing area that it's not as tied to structure, but you don't really require that all sources are linked here, but you just have how many sources can are linked without a certain congestion. And there are super many results that eventually they haven't. But that's all I want to say. So thank you very much for being here.
Thank you. Any questions? Yeah, Max?
A question about, you mentioned at some point, because of the Eulerian stuff, that there's like something like strong embedding. I've always wondered if maybe we're looking at the wrong type of embedding for the embedded part. Do you think this will be, the structure theory might be easier to think about strong embeddings? Like maybe that perspective is just helpful, or if we're talking about vertex-disjoint stuff? Yeah.
Well, if you learn digraphs, vertex-disjoint doesn't make sense.
No, I'm not asking for Eulerian digraphs.
Yes?
I'm asking for the general problem in digraphs just embedded with strong embeddings. Does this make the problem easier? Does it make some parts of the perspective clearer?
I don't really think so, because the part that we try to prove here, where's the picture? This bit. We didn't care at all about how it's embedded. Any embedding would be fine. So there was no, didn't try to get Eulerian or non-Eulerian. Also, this Eulerian embedding only makes sense if you have a degree 4, otherwise.
You're not talking about Eulerian, I'm talking about strong embeddings.
Yeah. Well, we can't even prove any form of structure without any restrictions in the embedding. If you also require this to be strongly embedded, I don't see how it would make things easier, unless we would find the natural counter obstruction, right? But also if you ignore click minus, just as for tournaments, things become a little bit easier, but not much easier. So my feeling is maybe we were too ambitious, also to get carried away by initial successes like tangles and flat walls and so on. We're just thinking that there might be very similar structure theorem for directed paths, and we have this for the undirected case. So maybe one could go the other way around, just look at disjoint path and see, well, if you can prove this for surfaces, maybe what kind of vortex thingy could we add and still have an XP algorithm, what kind of apex thingy, well, apex would probably not be hard, and what kind of things we can then glue together, in which way retaining solutions, and build a structure sort of this way, right? And then see what happens if we don't have it. But as you know, even with Mike and many, just asking for what if you excluded the cylindrical grid with one extra edge, proved to be a nightmare kind of thing. Right? So we had a solution eventually, but it's much harder work than it should be.
At some point you mentioned that k equal 3 is FPT, whereas for
k equal 3 is unknown.
No,
K4 is open.
for
K3 is
K.
K. K is
yeah
for
for
3 it's
For some special case, right? I forgot which.
The half integral.
Half integral.
Half integral.
Yes.
Yes.
And it's just polynomial time. I mean, because k is 3, then FPT doesn't really make
Alright, yeah.
any sense.
Did,
Yeah. So
can you sketch how it works? Like it just rough, something rough.
yes, it's like this. So the
It's like this.
This is the solution.
Should have seen it.
the general point is you take a directed cylindrical ball, and I'm asking, so let's say we want to route the sources targets, and we want to find paths that sort of go into the wall and not end up in the same place in the list. Right? And then do the same here. And if that works, then we're done. This is the same as Irene and so on already proved. But what if you have a small separation? Then for k is 3, it means we have a 2 separator. So we have here the terminals, and here's a wall. Right? But it's only 2. Right? And the reason why k is 3 works is because 2 separations, even in directed graphs, they would uncross. If you have crossing 2 separations, you can uncross them. Actually, because it's directed separation, so we have edges going this way, but not this way. And if I had another one of order 2 in this case, yeah, you could uncross them in this sense. Okay? So,
What do you mean uncross? Like, okay.
so in the undirected setting, if you have 2 separations like this, so this is A1, B1, and this would be A2, maybe B2, and that's the graph, right? Then each of these corners is also separated. Right? You would separate this part from that part. And by submodularity, you mean the number of vertices in this side plus this side is at most the same. Which means you could, if these are not the right things because you want them to go across, you could take one corner and the other side, and this gives you progress usually. For directed graphs, the problem is a bit more complicated, unsurprisingly, because again you have a directed separation. Let's say you know edges this way, but nothing goes the other way. And you have one like this. Then only 2 sides are really separations, right? So this bit is a separation, because everything, that's called a bottom because everything goes this way, and that one will be one. But these 2 corners are not, right? Because you can just walk through. And that makes it more complicated. But if you've only got 2 vertices here, then you can still uncross them and push them. And this is essentially what happens. And in a nutshell, what it allows us to do this is we have a wall here, and you only have 2 vertices here. So if I want to send path through here, then they have to come out again somewhere. Right? So we have 3 edges where they come out. But they would start here, so 2 in 1 vertex and then here. And it's not too hard, you don't need the wall anymore. It's not too hard to analyze how this path can go from here to here. So you just ask sort of for cut vertices, and then the analysis is simple. And then you can just delete this entire side. You delete the wall, get a much smaller graph, and because eventually you get a graph of small directed tree width, and you have a colored version of the problem for small directed tree width. For 4 vertices, it doesn't really, because then the separations have order 3, and things go wrong. And for 5, you know, it can't work because it's NP complete.
Okay. So I have another question.
Yes.
So the on Eulerian graph,
Yes.
I mean, we're learning at directed graphs.
Mhm.
So does testing immersion fixed graph A's, is it at PT or is it for XP? Can you use your disjoint paths for something, or can you just find the irrelevant cycle and remove them?
Well, we haven't written this up. So for weak
Do you want to be off
inversions,
the record? Or
sorry?
Do you want to be off the record? Anyway.
Oh yeah, I've forgotten the record. Yes. I mean, for there's also the problem of weak and strong inversions, because
Oh yeah.
in the algorithm that we wrote up, well, we simplify things a little bit. But if this is a source, then it might have another path is just going through the source vertex.
Yes. Yes.
But for strong immersion, you would not want this, right?
Mhm.
So for weak immersions, I think it doesn't follow immediately from what we proved, but we could get this. It's more like the difference between disjoint path and folio, and we only wrote up the disjoint path thing. But I guess for weak immersions, we could prove this.
In FPT.
Yeah. For strong immersions, things are different. But I mean, Dario, well, he gave a talk here, right? So so we decided we first want to write up the null quasi-order proof and then worry about folio later. Simply because the paper is so long and there's so much energy you can bring up to rewrite a system proof again. But yeah, eventually I think this should be.
Any other questions? For that, let's thank